So let me start by congratulating Sourav on and being selected for this lecture. So to introduce Sourav, I think many of us know Sourav from his work. He's at the Department of Astronomy and Astrophysics at the Tata Institute of Fundamental Research at Colaba, Mumbai. He did his bachelor's in physics from Jagrati University in 2001, and then master's in IIT Kanpur. Then he did an MS in physics and astronomy from Northwestern University, and he did his PhD in physics and astronomy at Northwestern University at 2010. Then he was at the Department of Astronomy, University of Florida, up to 2014, and then from 2014 to 2018 at the Northwestern University at the Center for Interdisciplinary Exploration and Research in Astrophysics. He was as a research assistant professor again at the same department from 2000, I think together, right? Sierra fellow and research assistant professor. And then an assistant professor, he joined TIFR in 2018 as assistant professor. Now he's an associate professor. So he has worked in multiple areas. So Sourav was a theoretical astrophysicist specializing in the modeling of dynamical processes at various astrophysical scales, including extrasolar planets, compact object binaries, stellar dynamics, and star cluster evolution. Sourav has been a major force in several highly realistic numerical and theoretical models that have explained many key observations for a wide range of astrophysical systems that include understanding the dynamical formation of gravitational wave sources, predicting and explaining key questions in extrasolar planet formation and evolution that explain observations by Kepler and TESS. These are two space instruments. And understanding properties of compact object binaries detectable by Gaia. So has an excellent track record of predictions that come true in future observations. His models guide future observations and provide a robust theoretical framework for interpretation of a variety of observations, including gravitational waves and extrasolar planets. So we have Sourav here to give this lecture, and he'll be talking about the topic dynamical formation of merging binary black holes and the way forward. Sorry.
Am I audible? Okay. First of all, I would like to thank the family and the foundation for this really encouraging moment as a theoretical astrophysicist in India. And I'm really greatly honored to receive it this year. It really feels like Professor Peraiah, although he's not with us in mortal self, but he's still encouraging us to do good work in theoretical astrophysics. So thank you. I'm greatly honored. So today, as mentioned by Annapurni, I will talk about the dynamical formation of merging binary black holes and what I think can be a way forward. And I will talk about the uncertainties and how clues from some other telescopes and other sources can help us in alleviating some of these uncertainties. And I intentionally tried to make this talk accessible to students. So that is the target audience. So if there are gravitational wave experts, and if you feel that some of these things that I talk about are too basic, so please forgive me. All right, so we all know that ground-based detectors, LIGO, Virgo, and Kagra, and the collaboration has discovered a little over 200 gravitational sources now. Okay, and most of these sources are black holes. So in this picture, you are seeing that these blue dots are the black holes detected by LIGO, Virgo, Kagra. So through gravitational waves when these two black holes merge. These Orange dots are neutron stars, and these red dots are black holes detected through other methods. So electromagnetic signals. So some other source may be donating mass, and this mass gets accreted by the black hole, and you can see X-ray and radio emission coming out of the black hole. So these are the black holes discovered by those methods. And these are the neutron stars that were discovered also through these electromagnetic radiations. Of course, these discoveries of gravitational waves, they are interesting for many, many reasons. So a lot of people are interested, and their target question may be very different. So some people are interested in these sources and discoveries because they want to test the validity of general theory of relativity. Some may be interested in finding out some interesting cosmological parameters that affect the properties and observations of these sources. So my interest is different from those. So my interest is finding out the astrophysical implications of these observations. So if you observe these margin binary black holes or black hole or neutron star binaries, so compact object binaries in general, I am interested in finding out how astrophysically you can produce these objects, okay? And once we have found enough number of these sources, by looking at the distribution of their properties, can we say something about the, can it improve our understanding of how high mass stars evolve, form these binaries, create these marching systems, etc. Okay? So this talk is about that. So there will be mainly some parts. So I will first talk about the astrophysical formation channels to create these objects. The physical processes responsible for the dynamical formation channel. So I have worked mostly on the dynamical formation channel. It is close to my heart. And the dynamical formation channel by far can create a lot more interesting objects than the isolated formation channel. So I will talk about some of these key things. And then I will focus on a very specific type of black hole that dynamical formation channel only can create. These are called the mass gap black holes or intermediate mass black holes. Isolated channels are not expected to produce black holes in these mass ranges. And I will talk about the processes that can give rise to formation of these black holes. And then I will talk about some potential way forward that can alleviate some of the uncertainties that plague us, okay? So if you think about how to create merging binary black holes that would merge within the Hubble time and will be detected by LIGO, Virgo, Kagra, or some other gravitational wave detector through gravitational wave radiation, the most straightforward way you can think of is you start with two very high mass stars and in a binary, and then both of these stars become black holes, and the binary remains intact. And these black holes then emit some gravitational waves that takes away energy from the binary, and then these two black holes find each other and merge, create one black hole, okay? So that is the most straightforward way. And you will soon find out that straightforward doesn't mean simple, okay? There are a lot of challenges in each of these different stages. So if we take a very short course on single stellar evolution, so that's the first thing, right? So remember, you need two of these to create a binary, right? So at the basic, you have a blob of gas, and there is a core where fusion is happening, okay, that is creating a stable object. And at some point, the fusion is not enough and it goes out of equilibrium. And at that time, the core shrinks, the envelope, which is this yellow stuff, that expands, okay? And this is the so-called giant phase. Now, depending on the mass of this core, different outcomes can happen. So if the core mass is low enough, it can create white dwarf. If it's somewhere in between, it can create neutron stars. If it's above some value, it can create black holes. Okay. Each of these values should be taken with a grain of salt. They move a little depending on metallicity, etc. But that's the ballpark number. And another interesting thing is, before the star can create a compact object, they can often become really big. So this is like 100 times or 1,000 times the sun's radius, okay? And that becomes a major challenge in creating merging binary black holes. Another major challenge is during this compact object formation, stars lose a lot of mass. So this is the best of our knowledge. So there is a lot of uncertainty in the details of exactly how high stars end up forming compact objects. But this is based to our knowledge. So if you look at the initial zero-age main sequence mass of the star, that's the x-axis, and the black hole mass that it is expected to produce, that's in the y-axis. And for different metallicities, these are the curves, okay? So let's take any one of them. So let's say at solar metallicity, a 120 solar mass star will end up creating a black hole that's about 15 solar mass, okay? Just imagine how much mass is lost from this star. So what are the implications for this? So if you want a merging binary black hole, the first condition in isolation, the first condition is the binary must not break, okay? So whenever you have a lot of mass loss, the binary orbit will expand, okay? And at the time of formation, black holes often receive kicks because of asymmetries in the supernova explosion. If the binary is very wide, its binding energy is very low, and then if the black hole gets a kick, it's very easy to break that binary. Okay, you must avoid this. Then comes like two conditions that together is deadly. So one is that the binary must not merge before becoming black holes. Okay, so remember the giants are really big. So if they start out close enough to each other, then they will end up merging while they are still giants. And then you do not have a merging binary block. So they need to be well separated at the beginning. And then the final compact object binary must be compact enough to merge within Hubble time. Okay? And if you look at the behavior of gravitational waves, so this is basically the Peters equation that tells you the average evolution of the same major axis as a function of the mass of the binary, etc. So A is the same major axis, E is the eccentricity, mu and m are the masses. So you can see that they are dependent on the masses, but they have a very steep dependence on the separation and eccentricity, okay? Now, for zero eccentricity, just to get a feel of the numbers, if we plot the merger time as a function of the initial separation, okay? So this is in solar radius, this is in spiral time scale in gigayear, and this is where Hubble time is on these scales. That means this is the largest separation you can have for the black holes that would merge. But if you remember, before becoming black holes, stars can become 100 times or 1,000 times larger than the solar radius. That is there. There. Okay? So you start wide, you have to start wide, And then some magic, we know the magic, by the way, some magic needs to bring it down to this pink region. And we believe that in some cases, common envelope evolution can do this for you. So what happens there is the following. So if you have two massive stars, and one of them becomes a giant and it overfills its Roche lobe, basically the influence of the other star becomes stronger than the star itself, then the star cannot hold on to its mass and it will donate a lot of mass to the companion. And in certain cases, this transfer is not stable. So basically, the accretor cannot take all that mass that's given, and it can create a common envelope. And in this common envelope, in this dissipative situation, the orbit can shrink enough to bring it to this region of interest. And in fact, this has been shown to work after the first detection, the GW5914 by Chris Belczynski's group. So here, this is an example evolution for creating a black hole merger event like this. And what I want to point out is that at this point, the separation was about 3,780 solar radius. And after this common envelope, it became 43.8 solar radius. Okay? So very good. But one issue is that the common envelope phase is the least understood phase of binary stellar evolution, simply because it's very hard. So it is to really solve it well through with microphysics and detailed numerical simulation, you need to have access to very low and long time scales and also very small and large length scales that makes this problem intractable. And the state of the art is to look at systems that may lead to common envelope or may have gone through common envelope and try to study their properties and then try to parameterize the determining coefficients of this common envelope evolution. There is another way you can form binary black holes, at least in with some masses and some properties. It is called the chemically homogeneous evolution in closed binaries. Okay. So one of the problems that I mentioned is that the stars become really big before they become compact objects, right? So what if you could avoid that? So the reason the stars become big is because of the core envelope differentiation. But what if you could mix in the core and envelope continuously? So that can happen if two stars are in a very close binary and they are tidally synchronized, like the Earth-Moon system, okay? So what that means is that the spin orbital spin period of the stars is equal to the orbital period of the binary, okay? Now, if the orbital period is really short or the things are moving really fast, then the spin can overcome the entropy barrier that separates the core and the envelope. So you're constantly fusing hydrogen and creating heavier nuclei. And this then gets mixed because of centrifugal forces with the envelope, and fresh hydrogen goes into the core, and then you fuse that, okay? And as a result, so this is kind of a cartoon of this. So a normal evolution will make it big, create Roche lobe overflow, etc. But in the chemically homogeneous evolution is the whole star becomes helium rich. It never expands because there is no core or envelope. The whole star becomes a helium star. The whole star becomes a black hole, never filling its Roche lobe. Okay. Although this is really beautiful, it works only in a small parameter space. So the orbital period needs to be very short. The masses needs to be comparable to each other. Okay. So clearly, even if chemically homogeneous evolution can create um, uh, merging binary black holes without the help of common envelope evolution, it can create only a limited amount of parameter space, cannot explain all gravitational wave observations. A completely different way to create merging binary black holes is what is called the dynamical formation in dense stellar systems. Okay? Dense stellar systems we see all the time. Every galaxy has them. So we call them star clusters. So star clusters can be open clusters, globular clusters, nuclear star clusters. So these are basically gravitationally bound groups of stars. So this is a picture of a globular cluster. It looks really beautiful and peaceful, but inside, it's not as peaceful. The stars are revolving really fast. They're interacting with each other. They are colliding with each other sometimes. There are really strong gravitational encounters as well. So this is, by the way, a real n-body simulation and real positions and velocities that we converted into a movie. What are the red dots? So the red dots are white dwarfs. So we couldn't see the white dwarfs because they are too faint in optical, so we just colored. So let's try to understand pedagogically the main processes that actually control the evolution of the cluster and control the rate of production and the properties of the interesting objects that are produced through dynamics. So imagine that the star is moving in the cluster's potential. Okay. So if you have red, Binny, tremine, this is the smooth potential of the cluster. And every now and then, these stars can feel the gravitational perturbation of another star. This is part of the grainy part of the potential. And there is a small deflection in their orbit. Okay. And since this is a negative heat capacity system or a bound system, if a star initially is moving faster or more massive and has a little more kinetic energy than the other star, it will lose energy. If it loses energy, it will sink deeper into the potential, and then it will speed up. And as a result, it will have even more energy to lose. And this is a runaway process. And the cumulative effect of two-body relaxation and dynamical friction is mass segregation. Okay? So this is, by the way, it sounds really fancy and exotic, but this is exactly the same physics, well, not exactly, but kind of the same physics, why dust settles on the floor. Okay? More massive than the air molecules. So after a lot of random interactions, it slowly sinks deeper into the gravitational potential of the Earth. So now, imagine that in the cluster, you have a mixture of black holes and other stars. So black holes becoming more massive, they will sink close to the center. Now, what is the time scale for this? Okay. So if you look at, so the two relevant time scales are the relaxation time scale. This is the time scale over which significant changes in orbit take place. And the crossing time scale, this is the time scale for which, over which a star just crosses the whole cluster. Okay. And these globular clusters and nuclear clusters are very special if you look at the comparative timescales for this. So for a globular cluster, the crossing time is about 10 to the 5 years. The relaxation time scale is about 1 billion year, and the age is about 10 billion year. So they are dynamically relaxed. Now the mass segregation time scale, so this is the time scale over which the black holes come to the center. That is roughly the ratio of masses. So this is the average mass, this is the mass of the black hole, times relaxation time. So for example, if the average mass is about 0.5 solar mass, this is about 10 solar mass, then this is 1/20th of the relaxation time. So over the age of a globular cluster, black holes can come, do some interesting things, go out, come back again, hundreds of times. Okay? So that makes globular clusters so special. Also nuclear clusters. And this is just an example of a real simulation where I'm showing you the core radius. So this is the core radius as a function of time. You see every time there are these spikes, these are the most massive black holes coming to the center and going really deep into the potential. And then some interaction happens. Some of the black holes get ejected dynamically from the center, and then the core bounces. Okay? That's what we see. So what happens when these black holes come? So they interact strongly with other single stars or binaries. This is a real simulation where you were seeing that these red things, they were in a binary. This blue thing came as a single star. You can imagine that maybe this red binary did not have any black hole initially, and then the blue was the black hole. But in the end, you see that the blue thing got exchanged into the red thing. Okay? So initially, the black hole doesn't even have to be in a binary. So remember the first problem I said, there is a lot of mass loss. So high mass stars need to be in a binary and the binary must not break. That constraint is gone. So a black hole can very well be a single black hole, but it will still come to the center. It will find other binaries to interact with, and it can easily exchange into that binary because it's the most massive object in this interaction. For the typical masses, yes. So the red things are 1 solar mass binaries, both 1 solar mass, and this blue thing is a 10 solar mass cluster.
But one solar mass is enough. You wanted bigger mass.
No, so now at the end of this simulation, you have created a black hole main sequence star binary, and this can again happen multiple times. So this is how the process goes. The most massive black holes sink to the center the fastest. Okay. Then the black holes and black hole progenitors do not need to be in a binary initially, because ultimately you will produce them through dynamical processes. Then the high density at the center with all these black holes allows binary black hole formation through repeated exchange encounters, three-body binary formation. So like 3 black holes can come together at the same time. It's of course has a much lower rate than the first one. And then 2 become bound and the excess energy is carried away by the third black hole. And via gravitational wave capture, this is even lower probability than this, okay? So basically 2 black holes come to each other in a hyperbolic encounter, and the pericenter is short enough that there is a burst of gravitational wave emitted, which makes the total energy negative. And you can capture black holes. The other thing is that, so after you have formed this binary black hole, typically the binding energy of the binary black hole will be very high, okay? Or very large magnitude negative, okay? So that means breaking that binary through dynamical processes will be very hard. So once you form a binary black hole, it stays a binary black hole. And through repeated encounters, the orbits keep shrinking, okay? How far can it shrink? So it shrinks until it gets ejected. So after every encounter, there is a recoil, right? This is just from conserving angular momentum and energy. And this recoil is of order the orbital speed. Okay. So there is a limit to how much a binary can be shrunk in a particular cluster. So ultimately, what really happens is that the black hole binaries a star cluster can produce, the properties do not depend on the initial binary properties at all. It is totally determined by the cluster's global properties. What is the velocity dispersion? What is the escape speed, etc. And let's look at a rather dramatic example of this. Okay. So we modeled two clusters that are identical in initial properties with each other. Only one cluster, let's call it the red cluster, had initially all high mass stars were in binaries. And the black cluster, all high mass stars were single. Okay. For example, in isolated evolution, this black cluster will produce 0 binary black holes because none of the high mass stars are initially in binaries. So if I look at the evolution of the number of black hole binaries produced by these two clusters, roughly about a relaxation time after, they are identical because the star cluster has all the other properties that are identical. Okay. The same is true also for the ejected black hole binaries. So that, I'm sorry, there are too many lines, but you should look at this green line on these two figures, and they basically converge at the same spot. So let's try to understand with college physics. So in a star cluster, we can determine what the velocity dispersion is from Friedel theorem, right? So that will depend on the mass of the cluster and the position of where you are interested in. And the escape speed, we very well know, will be this. And then which binaries survive in the cluster must follow this. So the binary binding energy must be greater than the typical kinetic energy of interactions in that cluster. Okay. So that is determined by the velocity dispersion. And which binaries get ejected? So the recoil speed is typically of the order orbital speed. That must be the greater than the escape speed, which is given by this. So you can see that not only which binaries are interesting, which binaries can take part in interesting dynamics inside that star cluster is determined by the mass and radial position in the star cluster, and also how much you can shrink that binary through dynamical encounters is also dependent on the mass and the radial position of the binary. So this, of course, determines the separation and the in-spiral time after you have formed this black hole binary. Now, if you take a look at, so this is just this back of the envelope pedagogical calculations using a Plummer sphere. You can write down the expected, so the time scales of various processes as a function of the mass of the star cluster. Okay, so this is the in-spiral time scale. So if the star cluster is very low mass, you cannot shrink the binary enough. So after getting ejected, it takes longer to merge. Then mass segregation time scale goes like this. The interaction, this is the dynamical encounter between stellar binaries, goes like this. And this is the wedge that is the most efficient in producing merging binary black holes. Okay. And if you look at the mass function of globular clusters, exactly where the cluster is very efficient to create merging binary black holes. Nature is very efficient to produce globular clusters with that properties. See, or it almost feels like whatever the power be decided that let's produce binary black holes that will merge within Hubble time, and let's design a system that will be very efficient in producing these things, and let's make most of these systems with the properties that are the most efficient. I'm kind of dramatizing, but that just happens to be the case.
Current mass function of the group.
Yes, this is the current mass function.
But what happens to the early universe? Or
well, the low mass clusters will be dissolved.
It would be one order higher, right? Because you still have.
Agreed. So,
it's not conspiring as such.
It's not conspiring. So basically, the point I'm trying to make is I'm talking about efficiency. Okay, I'm not talking about the total contribution. So it may still happen that lower mass clusters, being more numerous in number, may end up contributing more. But I'm talking about efficiency per star.
That's the peak efficiency.
That is the peak efficiency. So, so now we have learned how to produce these binary black holes, and we learned about the two very different channels, isolated binary evolution and dynamical formation. Let's talk about, so dynamical formation, of course, everything is created through dynamical processes. You can have very massive black holes, you can have eccentric mergers, you can have misaligned mergers, all kinds of really cool things can happen. Due to interest of time, let's talk only about the high mass black holes, okay? So one thing that we know from whatever we understand of high mass star evolution is that from single stars evolution, we do not expect black holes to be more massive than about 40 to 50 solar mass, okay? And that is because, so here I'm showing you an example figure. So if you look at the initial mass of the star in solar masses, and this is the remnant mass, and this is zero metallicity. So this is ideal as it was easier to calculate. And the line that you should look at is this red line. So this is the white dwarf, neutron star range. And then the black hole masses grows. And then an instability comes. This is called the pulsational pair instability. And then pair instability, where the black hole mass basically goes down to zero. You basically have no remnant. The whole star explodes because of this instability. So as a result, there is a gap, okay? Roughly, so that where this kicks in depends on metallicity. So in this case, it's, I don't know, maybe 60-ish solar mass, and then there is a gap, and then it again picks up above 100, okay? So there is a gap between roughly 40 to 100 solar mass. So any black hole that's above 100 solar mass nowadays are being called intermediate mass solar mass black hole. And anything that's between about 40 to 100 solar mass are being called mass gap black holes, because we expect that black holes do not form in this range. And lo and behold, we see black holes in this mass range. And of course, now there are a lot of these systems. And here is one interesting personal story. So you can see me. Ilya was the moderator of a bet. So this is Daniel Holz, and this is Chris Belchinski. So Chris Belchinski, unfortunately, has passed away. And this is Carl Rodriguez. So back in 2017, when no such system existed, we predicted that within the first 100 detection of mergers, we will find at least one where the pre-merger black hole mass will be higher than 50 solar mass. And 1905-21 made us right. So this group correct, this group wrong. and Ilya gets a bottle of wine no matter what. Um, and in this case, both masses were in the mass gap. And this happened before 50 detections. So it's amazing. So how do you even produce this? So one thing that we predicted was repeated black hole mergers in dense star clusters. Okay, so the idea is very simple. You have two black holes. They formed normally, had normal masses. They merged, but this merger product did not leave the cluster. So now you can repeat all the interesting dynamics that I talked about, acquire a black hole companion, and then they merge. Okay? Now, this black hole has no responsibility to follow the mass gap, right? So these were normal black holes. These black holes could very well be in the mass gap. So in this case, you will find merger with a mass gap black hole. Okay, so that was predicted, and that I think we are seeing now. Yes, some kind of dynamical system. No way to, well, no believable way to find through isolated evolution.
Could that be younger clusters?
Yes, interestingly, younger clusters, it's easier to find them in younger clusters. So other possibility is this. So remember the whole prospect of instability comes based on the mass of the core. Okay. So if it is possible to create some kind of peculiar core envelope ratio through, say, collisions or stellar evolution driven mergers, where the core is really tiny, but it has a large envelope on top of it, then the core mass will not trigger this instability. It will become a normal black hole, but it is now surrounded by enormous amount of mass that this black hole can accrete and grow in mass. Okay, so this has also been proposed. But even then, you need a dynamical system because you need the stars to collide. Okay. So
you also need spirals or long calculation?
Mergers will also work. So in case of mergers, there is this complication. There is a lot of angular momentum, and it remains a bit uncertain how much mass actually ends up in the system. Collision is cleaner. So this is about the code I usually use. So I'm talking about this because in what follows, I will show a lot of direct simulation results. So it's important to me that you start believing this code. Okay. So this is, we call this code CMC Cosmic. Okay. So CMC is cluster Monte Carlo. We include all relevant physical processes in the code. So this is an approximate code. It uses the so-called Henon type Monte Carlo technique to simulate large N star clusters. So this is where I entered in serious code development, and I have been working on this since. So I will show you some example comparisons with direct in-body code. So direct in-body codes calculates the pairwise gravitational encounters. So the computational complexity goes as n squared, and then from relaxation it gets another factor of n. It's very accurate, but it's also very computationally expensive. So it's impractical to study star clusters higher than about 500,000 N within a reasonable time. So these are the comparisons. So in each of these panels, I'm showing some quantity produced by a direct in-body simulation called the Dragon simulation. They were the first to produce simulate a million star cluster, although it did not look anything like a globular cluster. They had to make it much puffier and less dense. So anyway, the comparison is what matters. So the black is our result, red is n-body. So this is the early, near about when black holes form, the mass distribution of black holes. This is the late mass distribution of black holes. You see that they compare really well. This is the number of retained black holes in the cluster as a function of time. They also compare really well. And this is Lagrange radii. If you do not know what Lagrange radii are, so this basically tells you the mass distribution within a cluster, and even they compare well. But what really is interesting is that in the direct n-body code, this, by the way, is the best there is at the moment. This n-body 6++ GPU. It took about a year on 160 CPUs and 16 K20N GPUs. So that was state of the art at that time. And using our code, we modeled it in 2.5 days on 48 CPUs. Okay, and we get really trustable results. So I said that I will talk about how to produce and what is the how to produce these high mass black holes, and what is the relative importance of these two different processes as the cluster evolves. Okay. So one thing that we found back in 21 is that if you somehow change the high mass binary fraction in a, sorry, high mass autocorrect. If you just change the binary fraction in high mass stars initially, then when there are a lot of high mass binaries initially, you tend to produce this more of these high mass black holes. So in that study, we simply did 1 and 0, kind of back in the example. But there we saw that the total number of black hole binaries remains the same, but the masses, it turns out, can be different. And this is what we found, that if you have initially high mass binary fraction, you produce these high mass black holes, low binary fraction, no. Okay. So we wanted to understand this, and we noticed that in these two different simulations, just because how the binaries were chosen, there was a significant difference in how many high mass stars were there in that cluster, in each of these clusters. Okay, so this was work done by one of my graduate students who graduated last year. So he did a bunch of simulations, keeping the stellar population fixed. So there is no ambiguity in what really is going on. You do not really have to read through and understand all this initial setup. So if you're interested, I can talk about them later. So we try to be as observationally motivated as possible. And let's look at some of the results. Okay. So this is the mass gap. This is, I'm showing you the histogram of black hole mass function. And you can see that as we change the high mass binary fraction, so remember, each of these clusters have the same number of high mass stars. Only how many of these high mass stars are in binaries is getting changed. Okay. So what we find is that it is important to put the high mass stars in binaries if you want to create high mass black holes through the collision channel. Okay.
So you have your primordial binaries.
Primordial binaries in high mass stars. And we wanted to understand this because this doesn't make any sense. Because I initially said that these binaries get destroyed anyway, black holes come and they do dynamics, etc. Right? Yes. So, so this is the time when like it's targeted to the students. No, but thank you. So this is early evolution. Okay. So to produce these high mass black holes through high mass stellar collisions, you need to only look at early evolution, right? Because high mass stars are not high mass stars anymore after about 35 million years. They have become black holes. Okay. So what we find in early evolution is that the number of high mass black holes per model coming from the collisional channel is correlated with the fraction of high mass binaries. Even the highest mass produced is correlated with the high mass binary fraction. And we wanted to understand exactly what is going on. And we understand it now. So this is because there is a fierce competition going on in young dense star clusters. Okay. So the competition is between how quickly these high mass stars will evolve and become black holes, and how quickly you can bring these high mass stars near the center where they can collide. Okay. There is very little time. So within 35 million years, you need to bring them in to collide. And being in a binary just makes the mass segregation timescale shorter by a factor of 1 plus q, q being the mass ratio. And that helps. Okay. So let's look at this figure. So this is the age of the cluster. This is the distance from the cluster center. So if you, so this orange has no binaries initially. Blue has all high mass stars are in binaries. What you are seeing is that all the high mass star collisions are kind of happening between 3 to 5 million years. Okay, so that's when the mass segregation of high mass stars have happened, and also the density. So that is, these two lines are density. These two lines, these four lines are Lagrange radius. So mass segregation has happened. So this orange and this orange, this is for all stars, this is for high mass binaries, and similarly all stars, high mass binaries. So you can see that clearly they are mass segregated and the density is at the highest. And at this point, the compact objects form, a lot of mass is lost from the stars, and then the density very quickly decreases. But if you wait for the overall evolution, if you wait for 10 billion years, repeated black hole mergers take over. So the contribution from repeated black hole mergers, that's these squares, and these were the collision channel. So ultimately, it has no coordination. Okay? And let me jump a little, and let's talk about whether there are any implications for LIGO. So if you look at the merger time or the redshift, then the binary, high mass binary related effects become interesting after about a redshift of 1. So it will be really interesting if we can expand our horizon a little more in LVK or in some future detector, and we will start seeing all these interesting effects. Now, very quickly, so most of the uncertainties, so how much time? 5 minutes? 5 minutes? Okay. So most of the uncertainties in our understanding in or predicting the properties and property distributions of binary black holes are coming from our lack of understanding in how exactly how high mass stars evolve and become compact objects. Okay, so the last stages of high mass. And there is no clear way to theoretically understand or simulate it from first principles, just because it's very hard. There are groups who try to explode or model supernova, and it's very hard. A much more promising way is to discover a large number of black holes with companions of different kinds. Okay, So far we have been talking about black holes with black hole companions in compact binaries so that they can merge and emit gravitational waves. Of course, there are other types of black holes that accrete, creating the extra binaries and radio binaries. What I'm going to talk about is black holes with other luminous companion objects that are in wide orbits and not mass transferring and will never merge. Okay, so previously we were blind to these things. We never detected them. But Gaia has given us a chance to detect them, detect at least the candidates, and then we can go and verify to follow. So what's the idea? The idea is the following. So let's say that you have a black hole and the luminous companion is going around in some wide orbit. Okay. So Gaia, through its astrometry, can detect this orbital motion. Okay. On top of that, if the orbit is close enough, then tidal effects can distort the star. Okay. So as a result, the projected stellar disk size will change as a function of the phase of the orbit. And you can also see photometric variation. So this is called ellipsoidal variation. On top of that, there can be relativistic beaming and self-lensing. Okay. So this is work done by another student, Chirag Chawla, who also graduated around the same time. So what he created is a very realistic simulation of population black hole luminous companion binaries. So these are all details of the initial conditions. So they are all observationally motivated. And on top of that, there are three key ingredients he added. So the star formation rate we adopted from the FIRE2 simulations. So this allows us to maintain the complex correlations between metallicity, crowding, position in the galaxy, and age, etc. We tried the two most widely used supernova engine, and we use kick distribution that's observationally motivated. And he predicted that by the end of mission, Gaia can detect a few hundred black hole binary candidates that have luminous companions in wide orbits. Just to put it in perspective, apart from gravitational waves, the other types of black holes, total black holes, I think is only in few 10. Okay. And Gaia, which has other interests also, it was not motivated to find black holes. Just by it being super, can produce a group of or detect hundreds of black holes, okay, that we have never seen before. Another interesting thing is, if you combine Gaia RV, Gaia photometry, and Gaia astrometry, and then also test photometry, Gaia astrometry, Gaia RV. So on this, I have not used anything that uses any other telescope pop-up. So if you look at this, it's all Gaia. But there will be significant numbers of candidates like here that is detectable both through photometry and RV. And this is where both astrometry and photometry, and then this is where both photometry, astrometry, and RV. Okay, so some of these candidates will be very, very well determined, well understood. And so recently we also looked at, so far we have been talking about black holes. We also looked at other compact objects like neutron stars and white dwarfs. So we predict that by end of mission, Gaia will find white dwarf candidates with luminous companions in excess of hundreds of thousands to a million. Neutron stars, a few thousand, and black holes, a few hundred. Okay. And it is still consistent with what we find in Gaia based on DR3. DR3 has some additional cuts that preferentially takes away all the black holes. So we predict using DR3 cuts, we find 0 black holes, but a few tens of neutron stars and about 1,000 white dwarfs. So all of these numbers are ballpark correct. So now two things that are very interesting about this Gaia compact object binaries. Okay. So if you look at, this is for rapid prescription, this is for delayed prescription. You can look at any one of them. Okay. So I am showing you the black hole mass and the metallicity on the y-axis. Okay. And these are the like dots are basically detectable binaries and their properties. What we find is that our predicted Gaia detectable population has a wide range in metallicity. Okay. Now, if we have a wide range in metallicity, and if we indeed can find hundreds of black holes, then in principle, we can beam them in metallicities. Now, once we know the metallicity and we know the distance to the source, so we can find the bolometric luminosity and effective temperature of the luminous companion that we see. So we can model that luminous companion very well and find out the metallicity and age of the system. So we can find the metallicity and age of the progenitor of the black hole. This is an information that is not easily available through any other method. Okay. So finally, we may be able to find a map that connects the progenitor properties to the black holes for wide ranges in metallicities. And that will help, I think that will help us remove a lot of uncertainties that still plague us for high mass resolution and compact object formation. Now, another interesting thing is the detectability or the precision of these observations in Gaia depends on the luminous companion's magnitude, okay, not on the black hole property. So what we find is that, so here, this is a function, as a function of mass, what is the intrinsic distribution and the observed distribution, observed being detectable, not really observed. And you see that as a function of mass, there is not much difference between the intrinsic and detectable populations. So that is really valuable in astrophysics, because often what we try to measure or what we try to find, the population, the selection biases depend on the population's properties. Okay? So for example, if you look at gravitational waves, it is significantly easier to detect gravitational waves from high mass black holes. Okay? So it is not easy to get back what is the intrinsic black hole mass distribution other than modeling. But
some distribution, right here, because you could be magnitude differences or luminous or mass of the companion.
So the detectability is dependent on the luminous companion's magnitude.
Yeah, but there could be any mass and any distance, etc., right?
Yes.
So how do you get the intrinsics and observed to be similar? Because they're far away, and if the companion is faint, so you won't be able to detect, right? So.
Right, but a faraway luminous companion will not have a systematically higher or lower black hole mass companion.
Systematics are across similar.
Systematics are similar. And this is really valuable, and this is only available in the Gaia black holes. So that kind of, and the path forward, I think, is why Gaia black holes are very interesting, is if we find large numbers of black holes spanning large metallicity ranges, and we get to know the connection between the progenitors and the black holes themselves, then we will be able to model the high mass star evolution much better with a lot more certainty, and that will end up helping us about everything. All predictions of black hole mergers, gravitational waves, X-ray binaries, everything. So in today's talk, sorry for being a bit longer than I wanted to. So I talked about the astrophysical formation channels. I talked about the physical processes responsible for the dynamical formation channel and why star clusters are really efficient factories of creating merging binary black holes. And I talked about the ways to create mass gap and intermediate mass black holes and a potential way forward through detection of large number of compact object binaries that are complementary to other compact object binaries we have been detecting through radio, X-ray, or gravitational wave observations. So, thank you.
A nice lecture. Now we can have some questions.
Thank you for the lecture, sir. Just in the last slide, I was wondering, you mentioned that there is an intrinsic distribution and the detectable distribution. So this intrinsic distribution is involving all of the black holes with all of the companions, or is it only with black holes with luminous companions, which Gaia was in?
Black holes with luminous companions in detached orbit.
So when we were talking about the merging black hole distributions, so we cannot really extrapolate this information there that this distribution could also be followed by those systems.
So if you are discovering merging binary black holes through gravitational waves, the selection biases of the detector is dependent on the property of the black hole mass, the property of the black hole themselves. Okay. So whenever the selection bias is dependent on a property of the thing that you are trying to discover, then your detectable population will be significantly different from the intrinsic. Okay. So I'm sure there are merging binary black holes with all ranges of masses. Only it's much easier for LVK to detect high mass black holes. So LVK is sensitive to high detection of high mass black hole mergers to a much larger redshift, which basically makes the volume of the observable universe for large black hole masses much bigger. And that's how the selection bias works. But in case of Gaia black holes, the black hole you do not even see. All you see is the luminous component. And what is the astrometric precision? That depends on the magnitude of the luminous component. So Gaia and its astrometry does not care at all about the black hole's properties. So if you find a large number of these objects, then it is expected, and that's what we also find in our models, that the intrinsic black hole population will be similar to the observable black hole population.
Thank you.
Thank you.
Yeah. So, what is the role of core collapse in nuclear clusters? Does it accelerate, aid, or anything to the emissions or binary formation?
Right. I will first qualify what is core collapse. Okay. So core collapse is like different people use core collapse differently. So basically, what core collapse means is since this relaxation and dynamical friction leads to a runaway process, it just speeds up this sinking black holes, and then at some point you should hit singularity. So that is core collapse, but then something else takes over and the core bounces. Okay. So that is basically the dynamics. So you take the black holes, you bring them together. So these black holes do core collapse and then do interesting dynamics, and then the core bounces. Okay. But it is different from the traditional observer's core collapse. So if you look at the surface brightness profile for these clusters, while the black hole is doing all the dynamics, it will look like a normal, non-core collapsed surface brightness profile. Because the other stars do not care at all about what's happening deep into the center. It's dynamically decoupled when they're doing the dynamics. And then some of these black holes are ejected, and then the black hole mixes with the population. Actually, in a 2017 paper, I showed the surface brightness profiles of a cluster deep into the black hole core collapse and outside the black hole core collapse. And the surface brightness profile looks identical. We now believe that the observed core collapse clusters are those that have ejected most of these black holes and now have entered the contraction phase or the stellar binary bar.
Black hole forms without mass exchange, but it is
Chemically homogeneous.
So I'm just wondering how common are these?
There are some binaries that are proposed to be chemically homogeneous, but there is no clear evidence. And definitely there is no clear way to say that this black hole binary came from chemically homogeneous evolution. So theoretically, it looks like this is plausible.
So another diagram where the mass with the what's the lowest mass for?
So 20, I don't know, I will call it 25.
Any questions online?
Yes, one question.
Yeah, really interested.
You can ask questions.
Hello?
Yeah, you can
Yes, we
please
can
ask
hear
your
you.
question.
Oh, can you hear?
Yes.
Okay, sir. Okay, so thank you for very interesting talk. I was just wondering that these very processes, dynamical processes, which you mentioned about the formation of compact binaries and then black holes and then their merger. So this would continuously change the gravitational potential of the star cluster, and which in turn would again affect these very processes. So do you need to upgrade? I'm not sure about the time scales, but do you need to upgrade the stellar cluster gravitational potential?
That is an excellent question. So indeed, so I have so far talked only about what the cluster is doing to the black holes.
Yes.
The same thing is happening also the other way. The black holes are doing to the cluster.
Yes, sir. Yes.
So the black hole dynamics. So actually, it's so significant that this can be a separate talk altogether. Okay. We have found that if you have a little too many black holes in a cluster, then the whole cluster can dissolve. This is not surprising, actually. So if you take a 1 million solar mass star cluster,
Yes.
assume some easy to compute, let's say plumber sphere, it's just easier to calculate the total potential energy. And then you take one binary black hole with 10 solar mass and 10 solar mass and find out how much energy you can extract from this one binary black hole. Find that the one binary black hole will have more energy than the whole cluster.
Okay.
Okay.
Yes.
So indeed, black holes affect the cluster dramatically, and we have written papers on it. This is a very good question, and in our presentations, we do take these into account.
Okay. Thank you.
Yeah, Chatterjee.
I was confused when you said black holes will be affected by the envelope branch. So why they have to be affected? How the black holes are affected now? And also another question, What was Lagrange radius again?
Okay, so the first question, so this is about what Gaia has done so far. So what by end of mission, we say that, okay, so Gaia will observe for 10 years. So that is the baseline. And then it will collect a lot of data that will improve the precision, etc. So if I take into account all of this, then this is our prediction. Okay. Near the end, I talked about the DR3 prediction. So DR3 does not have all the observations yet. So they have only a limited amount of observation. I believe it's about 3 years of observation. And of course, the precision is not at the end of mission level. And since it starts off at 3 years, we cannot really detect binaries that have orbital period greater than 3 years because it will not be a full orbit. So taking into all these considerations, and then DR3 specifically put a cut saying that if the astrometric mass function is above certain value, we are not going to release it. Okay. So this is because they thought that maybe there were some spurious sources, etc. Okay, so if you take into account all of these different things, then we find that although by end of mission there will be hundreds of black holes expected to be detected, in DR3 there are none. Okay, and then the Lagrange radius. So so the star cluster has a distribution of stars. Okay, and let's say that you are interested in the 10% Lagrange radius. That is a radius of a sphere within which 10% of the mass of this whole cluster is contained. Okay. So if you know what is a half mass radius, that is the 50% Lagrange radius.
So why was the observation?
Which one?
Embody. Yeah, compare embody and CM.
With the red is CM.
Red is embodied.
Red is embodied. Oh, then yours is fluctuating.
Yeah. So basically, if I remember correctly, that is the some very low Lagrange radius, like 1% Lagrange radius. So at that point, so the whole assumption of Monte Carlo is that you have enough number of stars so that the relaxation time scale is long compared to the crossing time. So if you are looking at a very tiny sphere, a very low Lagrange radius, then the number of stars is not very high, and that creates a lot of fluctuations. Okay? So the fact that the average depth of the Lagrange radius is comparable to the n-body average depth is what we would call reasonably good evidence.
Samit.
So this that could also be given to the mind.
Right, that's also a very good question. And this is related to the repeated merger consideration. So the black hole spin distribution or bar spin distribution does not affect the overall cluster evolution much. Neither does it affect the strong binary mediated encounters. But what it affects is what kind of kicks it will receive after two black holes merge. Okay. So remember, in repeated black hole merger, two black holes merge, that merger product needs to be retained in the cluster, and then it can merge again, okay? So depending on the spin distribution, these kicks can be very large or not so large, etc. So we do not make any assumptions in that regard. So usually the way we study it is the following. So initially we assume that black holes form non-spinning. So normal black holes form non-spinning. But if you have two black holes that merged, then it will have a spin that is dependent on numerical simulation, relativistic simulations, okay? And then if that merges again and so on and so forth. This may not be quite true in nature. So the normal black holes may also have some spin. We simply don't know. So when we try to study the spin effects, birth spin effects of black holes, we simply randomly choose these black holes, give them a spin, and then look at the merger. Okay? Because the black holes the spin does not affect the cluster evolution. We can post-process and stuff.
Sure. If you extend your calculation to lower ones, for example, pulsars, then how does it compare with the rest of properties? Assuming the pulsars are constant.
I don't exactly remember the results now. So Claire was a graduate student at Northwestern University. Now she is in CETA. So she looked at pulsars in globular clusters with some details. So the papers I was involved in, it looked like all the pulsar properties and the radial distribution in globular clusters, they make sense. They are in reasonable agreement with globular clusters. But I do not remember like what has happened after.
Just the kind of differentiation. So you assume that the luminous companion doesn't depend bias the black hole mass of the black hole.
It just comes up in the model. We did not assume. So by observed, I mean detectable. Detectable.
Some type of
Yes, it's like Gaia. What is the Gaia precision? Actually, do I have like an extra slide or something? There was a detailed. So these are the end of mission cuts. Okay, so the orbit must be less than 10 years because we want to see a full orbit. There is actually another paper that I wrote with Jeff Andrews that is like really well done. You see only an arc, and what is the probability that you can detect acceleration in that arc? Okay. But it's not that exciting. So we wanted to keep it to 10 years, and then G must be less than 20.
so that is why the luminous companions separate types.
Okay, that we haven't checked. So spectral type dependent thing.
Yeah.
That we haven't checked. That we haven't checked. That will be interesting to check. Maybe we can talk about that. And then this is the astrometric precision. So this is the projected size. And then of course this is the distance. This is basically you go from center of mass to the luminous companions thing. And this is the projected astrometric size of that orbit. And that needs to be greater than the precision or 3 times the precision. These are the two cases we consider. And then for black holes, we also considered another case where the error in the black hole mass determination, so this is coming from the astrometric mass function, etc. If that is greater such that NBH plus minus delta NBH is definitely greater than neutron star mass, then it's a bona fide black hole again. Okay? So it turns out that about 1/3 of all discoverable things will have that also. So they are definitely bona fide black hole candidates.
So in the interest of time, like maybe we can move on. And Sourav will be around till tomorrow evening, and he's in room number 135. So if you're interested, you can talk to him, and he stays in Bhaskara. So students can talk to him.
Yeah, Bhaskara 102 and IA 135.